In this video, we're going to talk about some definitions that you'll need to know for F325 transition metals. So we'll start off with ligand. And the definition that you'll need to be able to write for your exam is a molecular ion that can donate a lone pair of electrons to a central metal ion forming a coordinate bond. Remember, a coordinate bond is exactly the same thing as a dative covalent bond. If we have a look at a couple of examples, so we've got the chloride ligand. If you think about its outer shell of electrons, it will have a full shell of 8 electrons, having gained one from somewhere else. And it can use any one of those lone pairs to form a dative covalent bond. Water, again, 2 lone pairs. It's going to use one of the lone pairs to form a dative covalent bond. Similarly, hydroxide will have lone pairs around the oxygen. It will use one to form a coordinate bond. And there are many other examples of ligands, but the key thing is they've got a lone pair of electrons that can form a coordinate bond. So if you think about a metal, such as nickel, if we take a water molecule and it can use one of its lone pairs to form a coordinate bond with that nickel. It's this lone pair that's donated into the d orbitals of the nickel ion. We're going to look at monodentate and bidentate ligands. So for monodentate, what you need to say is so it can donate one lone pair of electrons to form one coordinate bond. Remember, that's the same thing as a dative covalent bond. And for saying that in an exam, you would get 2 marks. One for donates one lone pair and one for one coordinate bond. So if we look at some examples, we'll start with chloride. Even though it's got lots of electrons around it, it's only going to use one of these to form a coordinate bond with a metal ion. If we think about water, even though it's got 2 lone pairs, it's only going to use one to form one coordinate bond, because if you think about a complex such as this, if we put a water there, there's no way that it can physically fit itself round to form a bond with this other coordinate bond waiting to happen here. There are some other ligands that you might find mentioned in exams, such as this. Now this molecule could behave as a bidentate ligand because it's got 2 lone pairs, but when we put it with a transition metal ion, because this is a flat planar molecule, so let's look at those bonds again. If we put one of those nitrogens on here, we can hopefully see that the geometry of this molecule will not allow it to bend itself round to form another bond over here. So due to the geometry of the molecule, it can only behave, when it's with one transition metal ion, it can only behave as a monodentate ligand. However, we could class it as bidentate. It could form bonds to 2 different metal ions, and we'll look at that a little bit later in this video. Next, we're going to look at bidentate ligands. So following on from our definition of monodentate, what you would need to say for this is so a ligand that's got 2 lone pairs of electrons, that would be 1 mark, to form 2 coordinate bonds. So again, this definition is going to give you 2 marks in an exam. It's more likely that they'll ask bidentate than monodentate. So what we're looking for are molecules with 2 lone pairs of electrons that have the correct geometry to form 2 coordinate bonds. So the 2 that are very common are this one, which is 1,2-diamine or ethane. You might also hear it referred to as EN or ethylene diamine. I'm going to call it EN. You might also see this one, which is the ethane diawate ion. And this one's called oxalic acid, so we call this ox. Places where you'll find your lone pairs then is the nitrogens in this molecule and the oxygens in this molecule. Obviously the oxygens have got more than one lone pair, but I'm only going to show one. Next we're going to look at how these 2 molecules bond to central metal ions. So we start off with, let's put nickel in the middle. Draw your octahedral bonds around the nickel. Make sure that your bonds go from the nickel to the nitrogen, and then fill in the bridge. That's 1. Again, I'm making sure that the bonds go to the nitrogens. That's 2. Final one is there. So there I've got the nickel En3 complex. Similar thing with the oxalate ion. It's exactly the same process. I've identified that it's the oxygens that have the lone pairs. So I'm going to start here, put the oxygens on, and then I'm going to fill in the bridge. That's 1. That's 2. And that's 3. So again, a bidentate ligand has got 2 lone pairs, so it can form 2 coordinate bonds. Both of these ligands have the correct geometry, that means that they can fit onto the octahedral bonds around a nickel or other central metal ion. In an F325 exam, you might be given something unfamiliar. So if we look at these 2, these are the 2 very common ligands that we use. But in previous exams, OCR have been known to give you something unfamiliar, such as this molecule, which again, you'd have to look at that and decide that nitrogen will have lone pairs on it. It's got the correct geometry because you can see this kind of bridge shape in the middle. And then you just do the same standard thing. Draw your nickel, or whatever metal it is. Put the atoms on that have got the lone pairs, and then fill the rest of it in around it. See, I've now added 3 lots of this ligand around the central nickel. If you want some more practice with drawing complexes with bidentate ligands, have a look at the video on drawing examples of complexes with bidentate ligands.